Okay, phew. That's a lot of new concepts for those of you who have not taken statistics or machine learning before. Let's take a breather and recap what we have learned today. So first, we start off by having a data set divided into two partitions, like so. We have the training set. So this is when your friend tells you the not just how he spends his time, but also whether or not he successfully finishes 342 homework. That is, all the Y's are given. And then you also have the test set, whereby you are just given the X's, but the Y's you don't know. The labels are not given. And then we did some math and we showed the following. We measured the goodness of a model by using MSE over training set. And then we say that if you want to minimize the goodness of the model, if you want to minimize MSE, you do stochastic gradient descent. And what does this look like? And you will get the chance to implement this in your homework next week. So you first init your model parameters randomly. And then for each training sample, x1, x2, y, what you do is you first predict. So you get your while tilde, which again because we're doing a perceptron model, then the y tildes, the predictions are formed like so. And then after you predict and you get your while tilde, you learn. Because remember, for the training sample, you know the true label y. So what you do is you update your model like so, plus equal eta x1 1 minus y tilde y1 plus equal. Sorry, so I realized that some people in office hour were not familiar with the plus equal notation. So yeah, and we do the stochastic gradient descent updates where we are going opposite to the gradient, where the function we are taking a gradient over is just the squared error of one data point. So in your homework, you will be writing a for loop that performs these updates. And what do we get? And the end result is we have a trained model. So we have a W1, W2, theta that would hopefully divide the training data. Let's say the training data is like this. The hope is that we would have a model that minimizes mean squared error on the training data. So perhaps this line, it has it's the best you can do with just one line to divide the data set into two subsections. So now that you have the W1, W2, and the theta, once you have a model, what can you do with this? Well, test phase. So this is not going to be in the homework, but this is what you will do in the real life, right? There's no point in predicting against your training set. You already have the Y's. So now you would unleash your model into the wild, and then you would perform predictions on those data points where you don't have the labels for. And this is the error rate that actually matters. Like, say, you might be using your model to perform classification on real patient data. Did you misdiagnose the patient? Yeah, so recap of all the mini lectures that we tackled so far. We have an example of a biologically inspired computation. And then we showed that the perceptron kind of reminds us of how neurons are wired up together in the brain with simple units. If they are connected together in a smart way, you can get interesting computations. And then on getting good parameters, we breezed through some mathematical intuitions to say that, well, what we want to do is actually solve an optimization problem over training data. And the approach that we chose to use is stochastic gradient descent. That's it for this lecture. Thank you for listening.